Hey there everybody, Mr. Marek here, doing a little bit of advanced circuits with you. In this video, we're going to study how capacitors affect an electrical circuit. The first thing we might want to do is remember what a capacitor is and what it does. Remember that capacitors are devices which store charge and therefore will store electric potential energy. And primarily we study parallel plate capacitors. And so it shouldn't be a surprise that the circuit symbol for a capacitor is just two parallel lines, both of which the same size. Remember that differs from a battery because a battery has one side longer than the other. So when you connect a circuit with a capacitor in it, the capacitor is going to do things that will change the circuit over time. So we don't need to be able to calculate what's going on as a rate of time change. That involves calculus, but we need to be able to describe qualitatively what's happening. So the reason that capacitors will change a circuit over time is because the charge on a capacitor will change over time. So for instance, if we just take a parallel plate capacitor that's initially uncharged and then connect it to a battery, a few seconds later, or in this case 1 second later, it's going to collect a little bit of charge, but then another second later it's going to collect more charge. So because the charge on a capacitor changes over time, then the way that the circuit around it behaves will change over time as well. So that's kind of the big idea for today here. So let's suppose we took a capacitor and we wanted to charge it up. So in order to make this a little bit more general, we're going to insert a resistor into our circuit with a capacitor and a battery. And so we've got a switch there. And then at time t equals 0 seconds, we're going to close the switch. So when you close the switch, now the circuit is complete, charges can move through there. So since the capacitor is initially uncharged, it provides no resistance to the current. Basically, it acts just like a wire. And so the current through the resistor is going to be very high. So when the capacitor is not charged, it's like nothing's there, just a wire. So it's like a short circuit, in other words. So if we go a second later, now the capacitor is going to be collecting some charge. So positive charges, which are moving from the positive end of the battery to the other, or to that side of the capacitor, you're going to have positive charges collecting on that side of the capacitor and negative charges collecting on the other side. And so at time t equals 1 second, your capacitor charge might look like that. So now there's a potential difference across the capacitor. We're going to call that V subscript C. So because there's a potential difference now across the capacitor, that's going to reduce the current going through the resistor. And so now the current's going to be a little bit smaller. So basically what the charged capacitor is doing is it's acting like a battery that's placed in opposite polarity as our original battery. So now we've got the plus end of our battery facing the positive end of our capacitor, and so that's going to reduce the potential difference across that resistor, which is going to reduce the current. So basically, as the capacitor charges, it's acting like a battery that's connected in reverse. So if we go for a long time, remember long time is code for time equals infinity. That's different for every situation. But eventually, after a long time, the capacitor is going to acquire enough charge that its potential is equal to that of the battery. So in other words, it's going to be the same voltage as the battery. And what that's going to do is it's going to stop the current through that resistor completely. So remember Kirchhoff's loop rule. As we go around the circuit, the voltages all have to add up to 0. And so we have positive V, and then as we go the other way, we've got V get the opposite polarity. And so what that does is it causes the voltage across the resistor to be 0. So when that potential difference across the resistor is 0, then it's no longer going to allow any charge to flow through it. So once that capacitor is fully charged, it's kind of like a battery turned around with the same voltage as our original battery, or you can kind of think about it like a break in the circuit. It's basically blocking any charges from going through the resistor, and so it's just like we took and we erased part of the circuit. We broke it so there's no longer a conductive path. Capacitors kind of doing the same thing. So now that the capacitor is fully charged, now we might want to discharge it somehow. So we're going to draw a similar circuit. The only difference is we're not going to include a battery. We're going to have our capacitor that is already fully charged right there. And then we're going to connect it to that resistor. So at time t equals 0, our capacitor is fully charged, and it has a high potential difference across it. It's like potential V. So when we close the switch, we're going to have a large current through our resistor. So there's our switch being closed. And so again, it's going to give us a large current. So our positive charges are moving from left to right through the resistor. And so all the positive charges that are on our capacitor are going to eventually go to the other side. The capacitor is not like a battery. It doesn't have a deep well of charge that it can bring up from. So a lot of that, or all that charge, is going to very quickly be taken off of the capacitor. So a second later, the capacitor is being discharged. So there's fewer charge on it going from here to here. And so that means that the voltage across it has dropped. Since the voltage is smaller, maybe say it's V over 2, that means that the current through that resistor is going to be smaller as well. Just as if we took a battery and we replaced it with the battery with half the voltage. So the same kind of thing after a long time, so that means after everything has reached equilibrium, then the potential across the capacitor is going to eventually be 0, and that current is going to completely stop. At that point, nothing is going to happen unless we bring in a battery or something like that. So let's look at a quick example. Suppose I have a circuit that looks like this, where I've got 2 resistors, a capacitor, and a battery, and then 2 switches. I'm call my switches A and B. And initially, both A and B are open. And then at time t equals 0, we shut switch A. And the question is, what is the initial current through each of those resistors? So I just want to know what the current is at the second that switch is thrown. So the 5 ohm resistor is going to have no current because that switch next to it is still open. So since B is still open, then there was no way for charges to move through that 5 ohm resistor, so it doesn't get any current. So to find the current through the 20 ohm resistor, I'm just going to use Ohm's law. Do 10 volts over 20 ohms, which is half an amp. So right now, because the capacitor doesn't have any charge on it, basically it acts just like a short circuit. It's not going to provide any resistance to the flow of charge through it. So we might want to ask the same question when a long amount of time has passed, so like time's equal to infinity. Well, that 5 ohm resistor is still not part of a closed loop, so it still doesn't have any current through it. Now the current through the 20 ohm resistor is 0, because that capacitor being fully charged acts like a battery that has been reversed and put in that place. Or you can think about it like a break in the circuit. So after a long time has passed, nothing's going to happen in this entire circuit until something else is changed. So same circuit. Both A and B are initially open. And then this time, at time t equals 0 seconds, we're going to close both of those switches. And we're going to answer the same two questions. What is the initial current through each of those resistors? So the 5 ohm resistor is still not going to have any current. That uncharged capacitor, again, it's like nothing's there but a wire, and so all the current can real easily go through that capacitor. And so it's all going to bypass that 5 ohm resistor. And so because the charges will take the path with the least resistance, initially all of those charges are going to go through that path, and none of them go through this path. Now as the capacitor gets charged up, that's going to change. If we get a little bit of charge on our capacitor, like this, now some of the charges in the current will follow the path through that resistor, and the 5 ohm resistor will have some current. That current will increase as the charge on the capacitor increases. So let's go back to the 20 ohm resistor real quick. Do the same thing because the current through it, because the current through the 5 ohm resistor is still 0. Now here's where it's going to be different than it was in the previous example. What is the current through each of those resistors a long time later? Well, now they're just like they're two resistors in series, and so we're going to do our equivalent resistance, which would be 25 ohms, and divide the 10 volts like that. So now both of those resistors would get 0.4 amperes of current. So notice that the current through the 20 ohm resistor went down, whereas for the 5 ohm resistor it went up. So again, the charged capacitor is like a battery that's been flipped around backwards. Or you can think about it like a break in the circuit. So if we go through and we just erase that part right there, that's basically what the charged capacitor does as far as the current through all those things is considered. Same capacitor, same circuit. We're going to say that switches A and B have been closed for a long time. So this is the steady state situation where we have the 0.4 amp current through that circuit. The next question is, what is the charge on that capacitor? Well, we know that charge on a capacitor is C times V, and I know what the capacitance is. It's 10 millifarads, but we don't know what the voltage is. The thing we have to remember is the loop rule. Through any closed loop, the net delta V has to be 0. So since the capacitor is in parallel with that 5 ohm resistor, they have to have the same voltage. And I can use Ohm's law to find the voltage on the resistor. Just multiply the current through it, which we already found, times its resistance. And so that would be something like 2 volts. And so the 2 volts goes there into my capacitor equation, and we would get 0.02 coulombs of charge on our capacitor. And so you can kind of see in this example how both of these, wrong pin there, both of these resistors affect the capacitor. So the next thing we need to consider is what happens if we have multiple capacitors in a circuit. We're going to start out with a simpler case of a parallel combination. So when they're in parallel, two capacitors may look something like that. Each capacitor is going to have the same potential. Since they're in parallel, they have the same voltage, just like resistors did. The charge on each individual capacitor is still going to be given by the equation Q equals C times V. And so if we want to find the charge on the system of capacitors without having to do a whole bunch of extra work, the charge on the system would just be the sum of the charges on each capacitor, which might look something like that. So we can define the equivalent equivalent capacitance of a system of capacitors in parallel just by saying that it's the sum of the individual capacitors. So if the only thing that's important to me is what is the charge on both of these guys, well, then I can find the equivalent capacitance first and then multiply that by 10 volts. Or I could just as easily find them individually and then add them up. Just kind of depends on the situation. Now the more complicated situation is a series circuit. So that circuit diagram would show us a couple of capacitors in series. If they're in series, they have to have the same charge. The reason that they have to have the same charge, and it's kind of important that we know that, is because the charge on both sides of a capacitor is always going to be the same. So you won't have more charge on the left side of this capacitor than the right. You have positive Q on one side, negative the same Q on the other. Now the space in between has to stay neutral. There's no battery in between, and so the charge on the interior side of the plates, like right here and here, have to be the same. So since those have to be the same, and since these have to be the same, then the charge on both capacitors has to be equal. So let's investigate that whole thing a little bit more carefully. So here's two parallel plate capacitors in series, and then here are all the positive charges that already exist in the wires. Remember that wires, just like everything else, are made up of atoms, and so they already possess a lot of charge. So here's all the negative charges. So this is before we connect the battery to the circuit. So notice that they're all kind of evenly distributed. When we connect the circuit to the battery, I'm going to assume that the positive end in the situation is the left side. So this is the positive end of our battery. Then we're going to have a bunch of positive charges collect on the left side of the left capacitor. Well, that's going to pull the negative charges from the region in between over to the right side of the left-hand capacitor. And then the reverse would be true on the opposite side. If we get 6 negative charges over here, then we also have to have 6 positive charges over here. And then that means there would be 6 negative charges on this side as well. And then there would be some charges left over in the center, but overall the center of that whole system would stay neutral. So the big idea here is that each plate has to acquire the same charge. The other thing here is that the capacitors are going to affect each other. If you put a big capacitor on the left side and a small capacitor on the right side, well, that small capacitor is going to prevent the big capacitor from getting charged up as much as it might otherwise want to. So we have to remember that when they're in series, they affect each other, just like resistors did. So, kind of going back to our original circuit. Remember the loop rule, the potential difference across the system. So, if I just designate 2 points A and B, the voltage across A and B must equal the sum of the voltages across each capacitor. So, in other words, V equals V1 plus V2. So that's the loop rule. Voltages all have to add up when we go through a loop. Also remember that since the capacitance equation gives us Q equals C times V, we can rearrange that and get V equals Q over C. And so that means that this has to be true. Q over the capacitance of the system, or the equivalent capacitance, has to equal Q over C added together for all of them. And so that might look something like this when you take out the fact that the Q's all have to be the same. So the charge on any one capacitor in that system is equal to the equivalent capacitance times the voltage on the whole system. So we have to remember that C right there is the equivalent capacitance, and the Q gives us capacitor on all of the capacitors. That's the thing we have to remember. Okay, so let's work through a quick example. So you have a 20 millifarad and a 5 millifarad capacitor connected to the same 10 volt battery. We want to figure out the charge on each capacitor if we connect them in a parallel combination versus a series combination. So if they're in parallel, the circuit diagram might look like that. And so each capacitor is going to have a potential difference of 10 volts. So to find the charge, I just have to do the Q equals C times V relationship like that, and then do it again for the 20 millifarad capacitor. So each one's going to have a different charge because they're connected in parallel. If they're in series, the picture looks more like this. And we have to remember, big idea, is that each capacitor gets the same charge. And again, because they're in series, they affect each other. We need to find the equivalent first. So that would look like that. 1 over CEQ equals 1 over 5 plus 1 over 20. And so get a common denominator, add up your fractions, and then flip it to get the equivalent capacitance. Notice the equivalent capacitance got smaller than the two individuals we started with. And now I just use that equation, plug in the numbers, and we would get something like 0.04 coulombs. So that's the charge on each capacitor. So total, there would be 0.08 coulombs of charge in that series circuit. So here are the things that we need to be able to do. First of all, describe for a capacitor in a circuit how the voltage, current, charge, etc. can change over time. So that's qualitatively. You won't be asked to describe using equations how the charge or current or voltage changes over time, but we need to qualitatively be able to describe that. We need to be able to calculate values for all those things for steady states. So that's where time is equal to 0 or a long time later. Third thing we need to be able to do is describe and calculate values for capacitors in series and in parallel. So those are the three big things we need to be able to do with all this information. Our plan next time is to kind of explore a little bit of this in lab. So do try to do a little bit of practice and make sure you understand before you get to class. Thanks for watching. Ta-ta.